Vibration Analysis Rule 2, Harmonics in Vibration Analysis. Harmonics Overview. Harmonics occur when a waveform is repetitive but not a pure sine wave. In vibration analysis, harmonics are seen as a series of evenly spaced peaks in the frequency spectrum, each representing integer multiples of the fundamental frequency. These patterns are critical for diagnosing mechanical faults because they indicate distortion in the vibration signal caused by irregularities in machine operation. Common sources include looseness, misalignment, gear faults, and bearing wear. When a machine component generates forces that repeat periodically but with abrupt changes or impacts, the waveform deviates from a smooth sinusoidal shape, producing harmonics. The presence and amplitude of harmonics often correlate with the severity of the fault. For example, a machine with slight misalignment may show a few harmonics, while severe looseness can produce a dense harmonic family extending across the spectrum. Understanding harmonics helps analysts identify underlying mechanical conditions and prioritize corrective actions. Harmonics also provide insight into the nature of the waveform distortion, whether caused by impacts, clipping, or modulation. This knowledge is essential for accurate diagnosis and effective maintenance planning. Pulse train, square wave, clipped wave, distortion, repetitive impacts. A pulse train consists of a series of sharp, periodic impacts or pulses in the time waveform. These pulses occur when a machine component repeatedly contacts another surface, such as a loose part rattling against its housing. Because the waveform is highly impulsive and repetitive, it generates strong harmonics in the spectrum. The sharper and more frequent the impacts, the broader and more intense the harmonic family becomes. Pulse trains are often associated with mechanical looseness, intermittent contact, or structural resonance. In practice, the presence of a pulse train indicates that the machine experiences repetitive mechanical shocks, which can lead to accelerated wear and potential failure if not addressed. Analysts should look for evenly spaced peaks in the spectrum and confirm the pattern in the time waveform to diagnose this condition accurately. Square waves represent signals with abrupt transitions between high and low states, creating a waveform that alternates sharply rather than smoothly. Although ideal square waves are rare in rotating machinery, they serve as a conceptual example of how waveform shape affects harmonic content. A perfect square wave generates only odd harmonics, 1 order, 3 orders, 5 orders, and so on, because of its symmetry. In real-world applications, signals with rapid on-off transitions, such as those caused by electrical switching or mechanical stops, can approximate square waves and produce similar harmonic patterns. Understanding this principle helps analysts interpret spectra where odd harmonics dominate, suggesting a waveform with abrupt directional changes or periodic restrictions in motion. Clipped waves occur when a machine's motion is restricted in one direction, causing the waveform to flatten or truncate at its peaks. This distortion introduces sharp edges into the waveform, which in turn generates a full series of harmonics in the spectrum, including both odd and even multiples of the fundamental frequency. The degree of clipping directly influences the strength and number of harmonics. More severe clipping produces stronger harmonics and may also create transient spikes. Clipped waveforms are commonly seen in machines with mechanical stops, clearance issues, or severe misalignment. Analysts should recognize that clipped signals indicate physical interference or restriction, which can lead to increased stress and potential damage to components. Repetitive impacts are characterized by sharp, high-energy spikes in the time waveform, often accompanied by ringing or oscillation after each impact. These impacts generate broadband energy and dense harmonic families in the spectrum, sometimes including subharmonics such as 0.5x or 1.5x. Subharmonics occur when impacts happen once per revolution but with asymmetry or instability in the contact pattern. Repetitive impacts are typically associated with severe looseness, rotor-stator rubbing, or catastrophic bearing failure. Their presence in vibration data signals an urgent need for corrective action, as the forces involved can cause rapid deterioration of machine components. Analysts should use both waveform and spectral analysis to confirm the nature and severity of the impacts. Rotor kit demonstration. The rotor kit example illustrates how mechanical looseness affects vibration patterns. When the bearing pedestal is loosened, the rotor rattles within its housing, producing a distorted waveform with clipped impacts and asymmetry. The spectrum reveals strong harmonics at 1x and additional fractional harmonics such as 1/3x, indicating complex mechanical behavior. This demonstration highlights the diagnostic value of harmonics. By observing the waveform and spectrum together, analysts can identify looseness and quantify its severity. The rotor kit case underscores the importance of understanding harmonic generation and its relationship to machine faults, enabling accurate diagnosis and timely corrective measures.